Hi folks, in today's video we're going to talk about the all-important ideal gas law. This combines all of the previous gas laws that we learned, including Avogadro's law, Charles' law, Boyle's law, and Gay-Lussac's law. And it's all into one equation that covers everything about gases that we would ever need to know. The ideal gas law looks like this. On the left side of the equal sign we have P and V for pressure and volume. On the right side we have N, R, and T for the number of particles. R is the ideal gas constant, which we'll learn about in a minute, and T is for the temperature. P stands for pressure, and pressure is equal to the force applied over an area. There's a number of ways we can measure pressure. In the US, especially with our tires and our cars, we measure pressure in pounds per square inch, or PSI. In a lot of scientific applications, we use pascals, or the bar, the torr, the millimeter of mercury, but the one that we use for the ideal gas law is atmospheres, abbreviated ATM. V is for volume, and that is how much space the gas takes up. You can also measure volume in a number of ways, including cubic inches, cubic centimeters, gallons, fluid ounces. The way we'll measure volume for this equation is liters, abbreviated capital L. For the number of particles, instead of counting each individual particle, because particles are extremely small, and when we're talking on a larger scale, it's hard to think about particles by themselves, we use a unit called the mole. A mole is made up of 6.022 times 10 to the 23 particles, or in other words, basically 6 with 23 zeros after that. It's a very big number of particles, but it helps to bring things into the macroscopic world in which we can understand what we're talking about instead of at each individual particle level. R is our ideal gas constant, and that will always be 0.0821 liter atmosphere per mole Kelvin. That is kind of a correction factor that helps us to helps all this math to work out perfectly when talking about ideal gases. Temperature is a quantitative measurement of how hot or cold our gas will be. And as you know, we can measure temperature in a number of ways, including Celsius, Fahrenheit, and the way that we'll use in this equation, Kelvin. There are a couple types of questions that you might be asked about this particular equation. One type of question is very mathematical. You'll be given 3 of the variables and have to tell me the 4th. So for example, I could give you pressure, volume, and number of particles, and you would have to solve the equation to tell me what the temperature of the gas is. The other type of question you'll be asked is more conceptual. It's, if I change this variable and keep these other 2 variables the same, what happens to this 3rd variable? So if I change one thing, what happens to the other? What are the types of relationships that happen? And we can tell that very easily. So for example, if I increase the pressure, in order to increase the pressure without changing the number of particles or the temperature, I would have to decrease my volume. Or if I wanted to increase my pressure without changing the volume or the temperature, I'd have to increase the number of particles, so there's more particles hitting. Or if I wanted to increase pressure without changing volume or particles, I would have to increase temperature. You'll notice that as we're looking at changing this one variable, anything that's on the same side of the equal sign as that variable will have an indirect relationship, or the arrows will be going opposite ways. If it's on the other side of the equal sign, then the arrows will go up the same way. And that is a direct relationship. So just to go through these, if I wanted to increase the volume, I could do that by decreasing the pressure, or increasing the number of particles, or increasing the temperature, assuming that I kept all the other variables we're not talking about the same. If I increase the number of particles, then the pressure would have to increase, or the volume would have to increase, or the temperature would have to decrease. And finally, if I increase the temperature, then the pressure would have to increase, or the volume would have to increase, or the number of particles would have to decrease. And if it helps, if you're looking for one particular variable, here are all the types of equations you would have to use. So if you're looking for pressure, it's nRT over V. Volume is nRT over P. Particles is PV over RT. And temperature is PV over nR.